Right now, you are processing a continuous stream of reality. You are hearing the tone of my voice, reading the text on your screen, and watching colors shift in real time. But if you look at the physical hardware making this possible, like the rigid grid of integrated circuits on this silicon wafer, you won't find any sound waves or colors. You will only find millions of microscopic switches, and they can only do two things: turn on or turn off. That creates a massive engineering problem. We have to map the infinite analog richness of the human world onto a strictly finite piece of hardware that only understands base 2 math, zeros and ones. We bridge that gap without adding any new physical machines. Instead, we rely entirely on the rules of encoding, a blueprint that builds complex reality from the ground up, starting with simple mathematics. The foundation of this blueprint starts with the fixed-width binary integer. This is the lowest level of data representation, and it is used to encode simple, positive whole numbers. But hardware immediately runs into a wall. If a physical chip only holds positive charge states, how do you store a negative number when there is no physical way to write a minus sign? Computer scientists solved this using a mathematical workaround called 2's complement. To make a number negative, you take the positive binary integer, flip all the zeros to ones and ones to zeros, and then add a single one to the final column. By applying this specific manipulation, the computer knows the value is negative. This allows the processor to perform standard addition and subtraction smoothly, without needing any new hardware to recognize a minus symbol. Solving arithmetic gives the machine a calculator. To make that calculator useful to humans, we have to translate those mathematical integers into something we can read. We do that with character encoding. Think of it as a massive lookup table that assigns a specific binary number to a specific letter or symbol. In the early days of computing, the ASCII standard managed this for the English language by mapping characters to simple 7-bit numbers. If you typed the number 65, the computer checked its table and displayed the capital letter A. But because ASCII used such a small bit size, it only held enough combinations for English letters and basic punctuation. When engineers tried to map the alphabets of the rest of the world, they simply ran out of room. The solution was Unicode, specifically a format called UTF-8. By using a variable width encoding system, the table could expand dynamically, using up to 4 bytes for a single character. Today, Unicode provides a unique, standardized binary address for virtually every character, script, and emoji on Earth. It unifies global digital text under one massive mathematical index. This diagram translates visual space into mathematics. Reality is divided into a grid of pixels. Each pixel gets 3 binary integers representing red, green, and blue light intensity. At 8 bits per color, mixing them yields over 16 million distinct colors. A digital photograph is nothing more than a massive sequential list of these color-coded integers, plotted precisely onto a fixed coordinate grid. Text and images are static. Capturing the real world requires us to encode continuous physical motion over time, like sound waves traveling through the air. This graph shows sampling. To encode audio, a computer measures the amplitude of an analog sound wave thousands of times every second. Next, quantization rounds those specific wave heights into finite binary numbers. The rounding precision depends entirely on the file's bit depth. Motion works on a similar illusion. Digital video flashes a rapid succession of static image frames to trick the human eye into perceiving fluid movement. To ensure those image frames perfectly match the spoken dialogue, a structural process called multiplexing interleaves the encoded audio data with the video data, locking them in absolute synchronization. When you watch a highly emotional movie, your computer is really just processing a massive stack of encoded integers, racing through the processor frame by frame. Take a look at this sequence. Based on everything we've covered, what exactly does 01000001 represent? It is the decimal number 65. It is the uppercase letter A in ASCII. It is a dark shade of blue in a digital photograph, or a microsecond of lo-fi audio. By itself, a binary sequence means absolutely nothing. It is just electrical charges. The data only becomes reality through the context of the software reading it. We took millions of microscopic switches, like this vintage transistor resting on a 1942 penny, and wrote a set of encoding rules so robust that we can now store human art, history, and science on a single, unified physical medium.